All right, thank you for having us this evening. A little back on all this. Jack and I have been collaborating for a goodly while. Jack has written, when he was looking for some help, another author to write another book about projects. He had a beginning book, first one, and so I got recruited to help out with the electronics and a little bit of coding part of it. The book that we came up with has a whole bunch of different projects in it. They're all microcontroller driven. So everything we do is involved with microcontrollers in one way or another. So we have all kinds of things in here, but we didn't have an antenna. And we thought about it and decided that what we would do would be to develop an antenna that used a microcontroller. Well, what would that be? It's something that needed to be tuned, perhaps, or remotely controlled, and we came up with an idea for a mag loop. So I started looking into it, and I did some research on mag loops. Any of you had an experience with a mag loop? Oh, really? None. Well, mag loops are kind of strange animals. They are small. They can be reasonably small. There are commercial units out there that you can buy, most of which probably work very well. They won't. So work in a different principle than most of the antennas. Antennas, the whole genre of antenna design and everything else is really interesting. It's very deep. It's a little mysterious for a lot of us. I designed several and built several different kinds of antennas. But the mag loop works a little differently from the dipole that you probably have hanging out in the backyard or the vertical, either way, in that it works on the M part of the electromagnetic waves. So the E part couples with the waves that come in, and they're usually resonant antennas. And you get a lot of noise because there's a lot of electrical noise everywhere. The loop, magnetic loop, is called that because it couples with the other part of the electromagnetic wave, the M part. And you can kind of think of it as sort of a transformer or a wire out there that gets in a magnetic field. And you know that if you have a wire in a fluctuating magnetic field, current is induced in the wire. And basically that's what's happening here with this loop. So we generate a coil, it's a loop of wire, and we make it resonant by hanging a capacitor on it, because that coil, it's got some inductance, and the capacitor and the inductor give you a resonant circuit. Well, resonant circuits are really neat because they give you a lot of response out for a fairly small amount of input. And that's what we have here. In fact, mag loops are very high Q devices. You know what a Q is? It's basically the sharpness of the resonant response. If you just build up a circuit with off-the-shelf inductors and capacitors, you get Qs in the order of maybe 10, 20, 30. Mag loops can have Qs up to 500. So they are very selective. And I'll show you some stuff in a few minutes. So we started looking into the whole area of mag loops. And we found out that they're very nice. They're small. We talked about working in a field somewhere and having to put up a big antenna. Well, these are small, maybe 6 feet in diameter or less. The downside of loops, there you see a plot over there of one of the loops, their frequency, and that shows the SWR. And you can see that if you vary very much from the frequency, the SWR goes up. That indicates that the loop has a very high Q. Now, the problem with most of these loops, and that's a problem with the ones that you buy, so you can go out there and you can spend several $100s on this loop that's very nice, it's small, it's made out of a coax, it's got a controller and everything else. And it's purported to work from 80 meters to maybe 10 meters or something like that. The problem with them is that they're very inefficient, most of them. And there's an equation out there that will tell you what the efficiency is for a given size. So if you take a loop that's size that you can carry around recently, and that was one of the design parameters. We wanted to develop something that was usable, had reasonable good efficiency, and was a size you could stick in the trunk and carry it somewhere. So if you take a loop that's 3 feet in diameter and you say you want to work 40 meters, it has an efficiency of about less than 10%, 8, something like that. And the reason for that is the way it's designed, there's something called radiation resistance. And the radiation resistance compared to the resistance that is coupled together with the ground and everything else is pretty small. And you end up with putting most of the energy heating the environment. So you put 100 watts in, and you get an effective few watts out on most of those antennas. So in the research that I was doing on that, I found out that there are some other ways to do this, and you can change the parameters. For instance, a bigger loop for 40 meters, something that's on the order of 6 feet to 10 feet in diameter, has a much higher efficiency, up to 50%. So you're not losing as much, but it's not very portable. You can't stick it in most cars. However, there are some designs that people have worked out in which you fold the loop over. So you take a 6-foot loop and you fold it in half essentially, and you get a double configuration. Well, the efficiency goes up maybe to 15%, something like that, or a little higher. And then there was another design in which you took 2 of these loops and you put them together. So you had a single loop over here, and another single loop over here, but they're separated a little bit and coupled together. You get an additional amount of efficiency. So I went through all of this stuff and some math and whatever else and came up with a possibility that what you could do is combine that together and create what we call the double-double. So it's actually 4 loops of wire, but 2 of them are hooked together directly and the other ones are folded around. So it gives the equivalent of a 6-foot diameter doubled in a 4-foot space. And we'll go through all the presentation of what we did. It was a neat project, and it worked out well. Now, there are some certainly advantages to this. Now, what comprises a loop, a magnetic loop? There are several parts together. There's the primary loop that I just described. There's the tuning capacitor. Of course, to get a resonant circuit, you need to have an L and a C, and you hope you don't have too much R. And then there's an impedance match, because these loops that you have tend to have a fairly high impedance. And we're working at 50 ohms. So you got to couple that together somehow and transform the high, maybe several hundred ohms, down to 50 ohms. Then you have to be able to tune it. So you need a capacitor that you can change. And it can be either a capacitor that you might find in a transmitter somewhere that's got a big plate spacing, I'll describe that in a little bit, and a controller so that you can remotely tune the thing. Now, there's another thing that you find, some of these commercial units, they'll show a guy sitting there, he's got his loop up on the table over here, and he's got a little dial over here, and he's changing that. The problem is, I've got capacitance, and so I get up close to the loop here, I change everything. This guy's got a really, really sharp resonance, and it only takes a few PF, microfarads, to change the resonance. So all of a sudden, it's not tuned correctly. So he carefully tunes it over here, the frequency one, walks away, signal goes to hell.
We've even got pictures of guys with wooden sticks Like this.
So you need some way to do this remotely, so you can put it over there. The other problem is you'd like to use a reasonable amount of power. I mean, most transceivers that you have are 100 watts. Well, the problem is that in this loop that I've got, and I'll describe it a little bit, you've got a couple of kilovolts, potentially at 100 watts, circulating around that guy. So you really don't want to get in too close to there when you got the key down and you got 100 watts going through there, there's 3 kilovolts, and you're trying to tune it.
With the defibrillator.
Yeah. Your own personal defibrillator.
Static damage some mouse devices too.
So we came up with this thing, and these are the parts. This is the double that I was talking about. So there are 2 sets of loops, tuning capacitor. This one happens to be one I found at a convention or something like that. It's got a pretty good plate spacing, which you need because you got high voltage going through it. Or you can use a vacuum capacitor, which is what I have up here. And the third part of it there is the coupling device. And what that is an impedance match. And there are other ways of doing this. You can use various different schemes. This is one that's real simple and it's cheap and it works well. It's called a Faraday loop. So that's where the energy goes, couples back through that loop, basically the transformer into the big loop, both directions. And, oh, there, a little lag. And you need a controller. So this is where the microcontroller comes in. So this guy has it's a remote control, and it basically tunes the capacitor. Well, it uses a stepper motor to change the plate or the rotation on a conventional, or to run the screw around in the vacuum. We use a micro stepper so that you get very fine control. And you need that because if you're moving the plates on the regular capacitor a little bit, it changes the frequency a fair amount. Again, that problem with the sharpening. Same goes with the vacuum cap, though it's a little less so. Now you need to know when you're at resonance. And there are a couple of schemes to do that. One is to listen for noise at the frequency where you are. So what you do is you tune it until you get the maximum noise without a signal there. Well, that's fine, except, you know, the guy on the other end is transmitting to you and you're listening to him and his volume's going up and down all over the place. You can't tell exactly where you are. The other way to do it is to read the SWR, because at the minimum SWR, you get the maximum signal. And you should be able to fine tune this and have presets. And ideally, what you'd like to do is have this thing work automatically. So you put a frequency in, push a button, off it goes. And that, in fact, is what we have. I talked about a little bit of this, that these portable antennas are always a compromise. And the idea was to minimize the compromise. And what we're able to do with this is come up with a better idea than most of the loops that you can find out and buy. The other thing we wanted to make sure is that you could transmit with reasonable power. Now, a kilowatt's a little bit much, but this was meant to be portable, and you don't want to lug your amp along. But 100 watts is very, very reasonable. And for portable solutions, probably good enough. So that's where we are. And I mentioned some of this stuff. Now, what we've done here is we start out with about 8% for the efficiency of a basic loop that's 3 feet in diameter for 40 meters. At 20 meters, it's got a little higher, but that's still not so high. But our arrangement probably is up to over 40%, maybe approaching 50 in a small portable thing. Now, it's not light necessarily, depending on how you build it, but it works pretty well. How well? Well, in order to figure out how well, come on. We did a series of tests. The test consisted of, first of all, running at a field day. So we did that and got pretty good results. We took it to a field day. It's been some years ago that we did. Nice day. We're sitting out in the field. This one is about, from here to the back of the room away from the road.
It was 75 feet.
Yeah. And so we were able to put it up there and work it. Setting up, super simple. Take the loop out, put it on top of the antenna, the tripod, and run your cable in. So you don't have to go shooting wires up in your trees, take your drone, or however you're going to do that.
The cable that runs from the controller back to this controller replaces the stick.
So we had a lot of success with that. The other thing we did was we wanted to make sure that it could handle the power we're after. And there are reports out there of people who build these things and all of a sudden they didn't work well, they get hot, maybe, melt the solder and whatever. The key to it is basically making sure you have good connections. Now, this is built up out of plumbing pipe. You can use other things. You can use coax. I've got some waveguide stuff that I got given to me, which is nice copper and bendable and so on. I'm going to make one of them out of that one of these days. But basically, it's a plumbing job. So all the connections are well soldered. You use heavy duty strap everywhere. Make sure it's all put together well. We tested it at 200 watts, left it on for a while, and it worked fine. No issues at all with overheating
Or arcing.
or arcing. Yeah, and that's a problem too if the plates in your capacitor are too close together. On the field day, this gives some idea of some of the contacts that we made. It was middle of the day, 40 meters, and the furthest one on this we got was Colorado. We weren't running all night with this, we just wanted to test it. And that was pretty good. We also did some others. We did an FT8 arrangement. And there, what we did, 150 contacts. And this one got out to Asia, all over. It was 50 watts going into the loop. And that shows you some of the contacts we made on this thing. I was pretty pleased with that. The third thing, moving it over. Well, actually, this is FT8 by distance. Now, what I was trying to do here is understand what we had in terms of a comparison. So this is the first part of that. We saw what the signal levels were by distance, and you can do that.
We need to tell them what they're seeing there.
Yeah.
The axes aren't very clear.
Well, okay, it's distance that way and it's signal level this way. So what we're trying to do with that is get a plot of where we are. And the idea was to do this with a couple of different antennas. So this was the first shot of doing that. Easy, a bit slow. The next thing, I think I may have, did I go too far?
Hit up arrow, go back on your keyboard.
Yeah. Yeah, here we are. So the next thing we did was to use Whisper. Now, if you're familiar with Whisper, it's a series of beacons around the world that you can get signal reports from, and they'll tell you where you are. The nice thing about that is it's quantitative, so you can tell. You send a signal out, you get a report on where you were in terms of signal level. And you can see that on the world map over there, Asia, down to Australia, all over there, even some down on the coast of Africa, down in South America. We tested both 40 meters and 20 meters on this. Had a whole bunch of contacts, and I'll show you that in a minute. And we compared different antennas. So the idea was to say, how does this compare with a dipole? Is it reasonably good? If it's got 8% efficiency running the same power in, you wouldn't expect a very close response comparison with those two. So what we're able to do is compare, for instance, on this one, you got distance going out this way versus the Whisper reports. And we've got an end-fed dipole, resonant dipole, compared to the mag loop. There's about a 2 dB difference on it on average. The way I did that was took a whole bunch of signal reports readings and plotted them up and see a distance this way. It goes from out to 20 kilometers, 20K kilometers, so, pretty much halfway around the world. And the signal reports are all over the place. But if you do a trend line through them or enough reports, you get some kind of a statistical measure of how the thing is doing. And you can see there's pretty much straight lines, both of them, but there's 2 dB difference between the two. And that tells me that the mag loop is a little less efficient by 2 dB than the end-fed. But that's actually pretty good for a portable antenna like that. So this one's on 40 meter. And this is a same plot, but not quite as far. So this one was just like the continental USA and around that instead of the world. Same kind of result, about 1.9 dB between the two. And we also did here you go, close in. Well, this is the same thing again. This was on 20 meters. There we had about less than a dB difference between the two. So it's a little more efficient at the higher frequency, and you expect this because the equations would tell me that for a given size, there's an optimum size, and the optimum size for this kind of an antenna for the size of it was sort of around the 20 meter range. So yeah, they're pretty close. And then we did a closer in still, another one, this again for the 20 meter, about 2 dB difference. And this is a sum up of what all we did on the performance. So if you look here, and we'll bother all the details of that stuff, but down here, you can see a comparison. And the comparisons are for everything. The double compared to a 6-foot loop was pretty close, but compared to the end-fed, which is really the measure of how good it is, it's about 2 dB. So the 2 dB was our measure there. And it's not a lot of difference whether it's North America only or DX. They're all within the range of less than the 2 dB. And that tells me the efficiency was in a range that made it useful. So the conclusion would tell us that nearly equal performance to a larger loop, which is not transportable, but about 2 dB difference to an end-fed, which is 130 feet long, not 3 feet in diameter. And it's easy to tune and works well for that. Okay, come on.
Just check your screen, just go off of what your screen is showing.
Yeah.
It'll catch up.
There we go. So the construction of this thing, I'll go through this quickly. Basically, I had a machine from Harbor Freight, which does bending of the tubing. And we made it up and then used PVC pipe to hold everything together.
Forward on.
It would come forward a couple on you, yeah.
Yeah.
Get to the right one on your screen and then it'll sync it.
There we go. Thanks. Okay. And you saw the Faraday loop that I showed up there. That's the coupling device, and we went through a bunch of stuff on getting the optimum size, and I won't go through that anymore. Then we invested time in building a controller. And a controller is kind of the heart of this thing that makes it easy to use and accurate. And you can see what we've got there. It's built around a little microcontroller called STM32, which is cheap. What are they, about $10, something like
Not
that?
even that, I don't think.
They run at a fairly high clock rate. They've got a lot of memory, a lot of pins out that you can use for various things. We use a graphical display, and I'll give a demonstration of this in a few minutes. And we have auto tuning. So you press a button, once you've calibrated it, put a frequency in, it goes to that frequency, and you're in business. And that's the diagram of it. So the parts of it are the controller. There's a signal source for doing the calibration. There's a stepper motor controller for the stepper motor, which is this little black thing up here. And basically it's a motor that goes around, but it moves a finite amount in rotation every time you give it a signal.
Hey, let me coattail that. The stepper motor rotates 1.8 degrees per pulse. But by putting a controller between the microprocessor and the stepper motor, putting this controller, we can divide that into 64 parts.
You can actually do more than that if you want to, but 60
Yeah, well,
is
66, no, we used 32.
32, yeah.
64 is what's capable. So you can take 1.8 degrees and divide it by 64. And that's the granularity that you can get with a
Rotational.
stepper motor. Yeah, rotating. But that, you know, tuning from one end of the band to the other with that kind of granularity is a career rather than a book. So we found that 32 on the controller motor was more than adequate. And what Al's talking about here is the more you use this thing, the smarter it gets. Because every time you sit on a frequency and you press the button that says where we want to be, it records where you are on the stepper motor versus the frequency. So the next time that you come in, 6 months later, it's stored in EEPROM. And if you type that frequency in, it goes and reads that from the table, just jumps right there without using that incremental tune. It just full bore goes to that point.
So yeah,
Is your stepper motor or controller an absolute distance that it's measuring, or
it's
is
degrees.
It's degrees.
It's
But
in
you have
degrees of
zero.
rotation. And you can get all different combinations of these things.
Yeah, we set it initially at 0.
okay.
And then,
Well,
And then-
to answer your question, the calibration routine
yeah,
has a positional endpoint, and there's a micro switch over there that tells it that's the beginning point. So it knows where to start.
And then it counts
Yeah,
steps.
it counts from there on. And I'll demonstrate this in a few minutes. We put it in a case. We did perfect board to begin with, and I got a printed circuit board afterwards. Those are all the parts to it. It's not really very complicated or very difficult to build.
and the software is free.
That's the completed unit. Got the graphic display, SWR readout as you go along, and manual tuning and automatic tuning, as well as I explained. And then and I'll let Jack talk a little bit here. He's itching to tell you.
Oh, yeah, this can't wait.
On the software side of it.
First of all, the design work was all done by Al. Al's the guy that's a smart guy, okay? And he won't tell you this, but I will. We authored an article for Radcom.
It's right there.
Yeah. Yeah. And we submitted it to QST. And at that time, Steve Ford was the editor. And he wrote me back and says, we have too many antenna articles. And so they turned it down. So I sent it off to Radcom. They published it in February of 21. And in 1922, we won the Bennett well, Al won the Bennett Prize for the most significant contribution to antenna design for the past year. And the really interesting thing is the royal sponsor for the Radio Society of Great Britain was Prince Philip. And our certificate was the last thing that he died or wrote before he died.
Wow.
So I think that's kind of cool too. Anyway, got nothing to do with anything. The processor, like Al said, it's a STM32F103, which is the most inexpensive STM family processor you can get. It's programmable in the Arduino IDE, which is free, and the libraries to run all the STM32 family code is free. So you got nothing invested in the software, literally.
Time.
And yeah, the chip, I think they still sell them for around $5. The AD
He's
5891 or something, no, 9850, the analog to digital converter. We selected that even though it was more expensive than the SI5351 that a lot of you are probably familiar with, because it generates a pure sine, whereas the SI chip is a square wave. And so we use that to generate the signals for doing the calibration on the standing wave ratio. Is there something?
Yeah.
But anyway, this, like I said, this whole unit probably is around $30 to build. And I've seen ads where they're selling 1,500. So ours is a bargain and no more doing that. And you can do that with any controller. This controller could be configured to work with any mag loop. And like I said, Al did the hard part. My part was really just writing the software for the display and getting the stepper motor to play nice with the antenna's vacuum variable capacitor. EEPROM is kind of a cool feature. It's just
You've got a couple more things if you want,
like the end.
features. Easy calibration,
Oh,
multiple band.
okay. By comparison, this thing really is easy to calibrate because we use the code and the oscillator that's built in and the micro switches too. So we know where we are at any point in time in the travel of the motor. 3 bands, 40, 30, 20, preset frequencies. We have 10 of those EEPROM frequencies that you can preset. So if you check into a net every day, you can come on, press the button, a preset button, off you go, you're right to your right place. There's an auto tune, which if it's a new frequency and has no idea where to go, it'll read through the EEPROM list, pick the closest one, here's a frequency, and then it'll zero in on the resonance point where the minimum SWR is. And then it'll write it to the EEPROM. You calibrate by hand if you wish. We never did that. It's written all in C code. All of the projects that Al and I do are open source. So you have open source for both the C code and the hardware as well.
Practical display.
Yeah, very good.
Right. Well, this just goes through.
Yeah.
So, conclusions?
Conclusions is I think the hardware is the key to the efficiency of this thing. And we actually can get over 50% on some frequencies in terms of efficiency. the graphical interface just means that you don't, it's much easier to tune and way faster. You know, if you're in the basement and your antenna's in the attic and you've got to move that thing by hand, you're gonna get a little cranky. Oh, yeah. Yeah.
Did you experiment any with different diameter copper? I've read in some places that. the
yes.
diameter
Yeah, that does make a difference.
improves
But
efficiency.
then as you go out this way, the cost goes this way.
The weight too.
It goes.
Yeah, way fast.
Yeah, what you don't want to use is real small diameter.
Is that 3/4 or?
It's half inch.
Having.
I also tried a triple double, so I did 3 at one point. And it increases the efficiency a little bit, but it isn't worth the extra weight. So, yes,
Now, I myself am really concerned about MOS devices. I tend to, when you talk about the power of your transmitter causing high voltage there, I think if you're receiving and you get a solar flare or something like that, that you could get something coming in the other way.
well,
I myself don't like really static sensitive devices because of them being blowable.
yeah. Well, there's a large degree of isolation between the electronics that creates the signals to tune it and the actual high voltage or whatever. There's a controller in between, so there's no way that you get that unless you got a direct hit, and then everything goes. We run it for hours and hours and hours, and have not had any problem in wintertime or summer or whatever. So it's not very vulnerable. And in fact, we've done about 30 projects here, and we've spent 4 years on building the P41, which has a nice little microcontroller in it. I've blown a few of them, but not because of static electricity, but because I was messing around with things and I wasn't, I shorted it out or something. Not had any problems with that.
Well, the other advantage that we noticed when we took this out and played with it at field day, we didn't hear anybody else. And everyone else that were using dipoles and verticals and so forth, they were bitching each other because they were cross feeding into their signal.
It's wide enough for voice communications.
Oh, yeah.
Yeah, and see, the reason, and what Jack was saying is because of the high Q of the device, signals outside of the very narrow bandwidth you've got very small amplitudes. So you don't get overload from the guy who's sitting next to you at the close frequency. That's an advantage. Can you bring the camera over and
Yeah.
I'll give you a little brief demonstration of what we got here.
Put that on him.
Oh.
So we can see him. And I'll get up close here.
Maybe.
We're good.
So if you bring up the camera there,
Well, you're still sharing your screen.
No,
So yeah, if you unshare your screen, then we can put it on.
Can do. Up here. Whoops. Come on.
Are there any things like common mode issues, common mode currents? Or-
Never found anything.
We've never run into that.
Okay.
That doesn't mean it doesn't exist. But we're so careful.
So they. Shocking. So what's typical VSWR that you're tuning for?
We get it down to almost always at least
1.1, 1.2.
1.2 to 1.1 at resonance,
You're fine.
but it can be as high
All right.
as 6 to 1.
But so what we got up here is a demonstration. If you zoom in on this over here, capacitor, that this is a Russian unit when you could buy stuff like that. It took a long time to get it. It wasn't very expensive. It was less than
On
$100.
the right thing or?
Yeah, this right here.
Oh, okay.
So that's the capacitor. It's variable. And basically, it'll handle high voltages very nicely. It rotates, this rotates, and there's a screw in there and moves there's two pieces concentric and moves them back and forth. Gives you the change in capacitance. This guy here is the stepper motor. That's the one that Jack was talking about that has a very high rate. It'll handle a lot more torque than we got. This is basically not anything. We bought it because it has the high resolution. This mechanism over here has really one purpose, and that's to set the limits so that because this thing rotates, it rotates, I don't know, 30 or 50 rotations from one end to the other. You got to know where you are. So it got a lead screw and this follower, and then there's a micro switch on either end. So you can find out where the beginning point is. There's an end point measure too in case you go too far. In the calibration, what it does, first thing it does is find the beginning point, sets the counts to 0, and then it starts from there. And then calibration, you tell it the frequency you want. It hunts until it finds the minimum SWR, records the value of the counts, and says that's where it is. Aha. And what we do is we do the band ends. So you start at 7 megahertz, you go to 7.3, then you do the 10 meter or the 30 meter 10 megahertz, and then 20 meters from 14 to 14,350. And it stores all of those things and know where the bands and ends are, and that's the starting point for it. Then when you put a frequency in. Now what I have here, I didn't bring a mag loop along because it's kind of big. It is transportable. I wasn't up to carrying it around. So this is a coil. It's an air coil, has very low losses. This is the coupling device, the Faraday loop, and it's hooked in parallel with the capacitor. So basically, this is resonant with this capacitor from about 6.8 megahertz to maybe 15, something like that, with that capacitor. And what I'm going to do is a demonstration is I've already calibrated. I did that at home. It takes about 10 minutes to calibrate it because it goes step by step to find exactly where it is. So I won't do that. But what I will do is I'm going to use the screen over here, and I'm going to pick 40 meters, and then I'm going to pick a frequency. So what I'm going to do here is, well, I'm going to bring that. I can choose which of the digits I want to change. And I'm going to make it at 7.2. Now, I've chosen the frequency, and you do that, say, I want to listen to some guy here on 7.2. Then what I'm going to do is if you can put your camera over on that thing over there, I'm going to press the auto tune button. Starts rotating. Now, it got pretty close to where it ought to be, and it's searching now for the minimum. And I think I may have bumped the coil in between. So it may or may not find it because it started at a certain point and then went on from there. But it's going to search until it finds the minimum SWR. And it's actually a lot faster than normal. Yeah, it'll find it here. Because the calibration was done at home and traveled this thing out here, I changed all the parameters and didn't know where it was. It's going down. So
Yeah.
the SWR was at 12 to begin with. It's down around 8 now. And it's at 7. So when you're doing this in a calibrated environment where you are, it goes a lot faster. It takes just a few seconds. Again, I didn't take the time to calibrate it first. SWR is down about 3. There we go. You can see it. Now, when it gets within 3, then it
You're
goes into it.
you're just arriving in the attic.
So it does a different routine. It doesn't jump as far, and it does a fine tune. And it will finally get down to, well, it's at 1.4 now, still going down. Okay, it found the minimum. And it's going to go back because it goes past it and then comes back and iterates on it. So it found the frequency. And I can do another one of these simply by either pulling up one of the presets or whatever I'm going to do. And it gives me a plot. So this one's not quite as good as it might have been if you had a real mag loop over here, but it gives you a plot of the SWR. And you can see there it's about 1.5, 1.4, which isn't half bad. You get 1.4 on a dipole, you're doing really well. And you can see it's very sharp. Then I can do other frequencies in the same thing. Now, we only have 3 bands, and the limitation on the bands is really a limitation of the size of the capacitor. Megahertz with the size of the loop we've got, you'd have to have much less than that. Which means the residual capacitance would have to be down around 5 or something, which is not doable. And so you're limited to 2 bands. If you wanted higher bands, you'd have to have a smaller loop. If you want 80 meters, you'd have to have a bigger loop. It's just the physics of
Put
it.
your fixed capacitor in series with it?
Yeah, I guess.
Yeah, you did. Yeah.
Again, there's a problem with range. I've tried all kinds of things. The residual capacitance of the loop itself in conjunction with everything else is the limitation of where you can get to in terms of high frequencies with a given loop size. So, any other questions? Yes.
Are 40-meter mag loops not typically able to be used on 15?
Well, I'm sorry, 15 meters.
I don't think that.
Yeah, you'd have a hard time getting up to 15 meters. At least in the designs we worked with. But it wouldn't be too difficult to design a 15-meter loop.
Mag loops don't work as nicely as dipoles. Yeah.
The other thing that you got, and it's not a real great amount, but they are somewhat directional. So if you look at the plot of the lobes, there's a somewhat, maybe, I don't know, 4 to 6 dB, depending on the directionality. It's not real great, but there is some of it. But that's pretty cool because you can just rotate the whole thing very easily if you know what you're doing. Now, you can't get up the tree and do that so readily. Any others? Oh. Okay. All the information, if you want to do this, is in the book that you got here, and it gives the construction parameters, tells you how to build it, what to do, and build the whole thing.
There's
So
2 chapters of that.
one on the hardware and one on the software. Well, thank you very much.
Right.
Thank you.